Okay, so this is a crazy thing here. I'm here in a Uber car going to New Jersey,
Of all
eh,
places.
of all places, right?
Yeah.
And I know it's dark and you can barely see me, but hopefully the audio is good because I'm here with the amazing, the unique, the Java champion, Barry Burd. Hey Barry, how you doing,
There we
man?
are. I like it when the car in front of us turns on its lights.
Yes,
When
because
they hit the stop, when they hit the brake, then you can see me on this.
right,
Because,
exactly.
yeah, okay, that's cool.
It's gonna work,
Okay,
right?
all right.
Yeah. So the reason I'm kind of recording this thing in the dark here is because I was having a conversation with Barry, and he wrote a book about quantum computing. What's the name of your book, Barry?
Quantum computing algorithms.
All right, quantum computing, and so so we had all this discussion about quantum computing on the way to the user group, and now in the Uber, and I was like, man, this is so cool. So maybe we can talk about this a little bit. How about that?
What better place than in an Uber at coming out of the Lincoln Tunnel at night to have a discussion about quantum computing?
Right.
Yeah, that's
Yeah.
a great idea.
So yeah. So sorry that you cannot see us much, but who cares, right? So
Do you want me to try turning on my phone's light, my phone's
no, that's okay.
flashlight?
Let's
Okay, all right.
let's just
Okay.
go ahead. So
All right.
so here, one thing that I want to talk to you, Barry, about, right? So the last question I asked you. Let's start with the last question. I asked you.
Right. We'll
You know,
work our way forward.
Yeah, we're talking about quantum computing, and I asked you, is quantum computing a generic computer? We ever have a quantum computing in our desk and handing out mouse in our windows?
Right. And the answer is no. Quantum computing is very good at a limited kind of problem, and it's terrible, absolutely awful for general purpose computing. You would not want to do it. If I can't imagine being able to write a spreadsheet program in quantum computing, but even if you could, you wouldn't want to. It would be the most horrendous, the most inelegant, the worst programming you'd ever seen. If you could do it. I don't even know if you could do it.
All right, but why? What's the difference between a quantum computer and a normal
Because
computer?
a normal computer, we're used to generic building block steps. As much as we like object-oriented programming and functional programming, the bread and butter of classical computing, that is non-quantum computing, is loops and if statements. When you get down to the bare bones. But quantum computing, those are not the basic building blocks. With quantum computing, the basic building blocks are superposition and entanglement. And when you get a solution to a problem using superposition and entanglement, properties of let's say subatomic particles, when you get a solution to a problem, it's because there's some, what I would even call, coincidental similarity between the way certain subatomic particles work under certain conditions with a particular problem. So, for instance, Peter Shor discovered that there was a similarity between some operations that we could do with qubits, quantum bits, and factoring large prime numbers. And you could use that to break the RSA algorithm. And there may be some very, very clever people who know how to extend that to other interesting problems. But how often do you want to write a database program that depends on factoring large numbers into primes? You don't.
Right.
And that's a particular problem that you can solve with a quantum computer, but it's just not a general purpose problem. So that's where the world stands with quantum computers. They are going to be very, very impactful if we get the engineering right, say in the next 10 years, in terms of cryptography. But no, you're not going to have one on your desk so that you can work out your to-do list.
All right. So what would be the expected thing, right? So you're gonna have, for example, you're telling me that IBM, and some other companies already have like quantum computers that you can use online, to send problems to, right? So what do you think is the use case? Right, they're going to be, those like server farms of quantum computers that you can send problems to. How do you think this is going to play out in the real world?
Well, I don't want to make predictions that don't come true.
Right. Yeah.
Or predictions that are under predictions. You know, there's
Right.
the famous one: no one will need more than 64K.
Right. No, I'm just talking
something
about
like
more
that.
like general terms, right? So not really
I mean, I think
prediction.
there are specialized problems like searching with Grover's algorithm, and certain mathematical problems that we know how to solve now. There's a big field right now for a slightly different architecture of quantum computing for optimization.
Okay.
So what you do is essentially you boil up a bunch of qubits and let them kind of settle into an optimal low energy state, and that low energy state somehow maps to the optimal value of some real world practical problem. So I mean, there's these certain specific things that they're going to be really, really good at. And I mean, for example, the idea is that breaking RSA would take billions of years on a classical computer. It'll take minutes on a quantum computer once we get the engineering problems worked out. And I don't want to forget, apropos of nothing, to say, oh, we've got some light. Oh, look at that. All right, you can see me.
Right, okay.
I don't want to forget to say that you can program a quantum computer in Java. Johann Voss has developed the Strange API, and yes, the Java world is not blind to the existence of quantum computing. It's there, it's alive. I've given lectures on it.
Okay.
It's fun.
That's pretty cool.
Yeah.
All right, so I'm just kind of pointing me here just so you guys can see me a little bit here, right?
Yeah.
So thanks for bearing with us in terms of darkness here, but I think that should work a little bit better. Okay, so Barry, we're discussing before this whole notion how quantum computing works, right? So do you want to have like a quick explanation like you did before with me?
Sure. Imagine 5 bits. What does it represent? It represents a 5-bit number. Big deal. 1 5-bit number. If you wanted to talk about 1,000 5-bit numbers, you'd have to have 1,000 registers of 5 bits each. A qubit can be in a superposition state, a state of superposition, wherein it, in a way that I better not try to describe too specifically, wherein, when it's in a superposition state, has properties of being both 0 and 1. And if I say that it's 0 and 1 at the same time, the physicists will go nuts and clobber me. So I don't want to say that.
Right.
But the idea is that a single qubit can sort of, in some way, represent zeroness and oneness at the same time. Now imagine that you have 5 of these. Well, if one of the qubits represents 0 and 1, another represents 0 and 1, and you have 5 of them, then there are 32 different combinations of zeros and ones that they can represent. So you have 32 values at once that you can deal with. Okay, 32 isn't a big deal. If you have 10 of them, you have 1,000 values that you're dealing with at once. The idea is the more qubits you have, the number of values that you represent at once grows exponentially. And I really do mean exponentially in the mathematical terms, not the way people use it as just meaning big.
Yeah, it's not really big, right?
It's really exponential.
It's really exponential,
If you have 10,000 qubits, you have an enormous amount of information represented at one time. Now then, the trick is, let's say you have 10,000 qubits, you have all these numbers being represented at once. How do you manage to ferret out the number that you're looking for, the one answer to the problem that you're trying to find? Well, that's a very complicated choreography. But with something called entanglement, you can sort of impact more than one qubit at once. You can impact many qubits at once. So you have to kind of devise this quantum algorithm that takes all these values at once and somehow makes it so that when you measure this system, you are very, very likely to see the correct answer to whatever problem it is that you're seeking.
Okay. All right, but is that like, when you say you're very likely, is there like a statistical issue around it, or is that you actually going to have like a real final answer?
You're going to have a final answer to within whatever probability you're seeking.
Right. Okay. So
how important is it to you?
All right. There's a probability.
If you don't really care, well, you'll do the experiment a few times and say, I think I've got a good enough answer.
Right.
But typically, I mean, even when I do a problem with students, we do what's called 1,000 shots. We run the same circuit 1,000 times and see which answer is most prominent.
Okay.
And even on real quantum computers that we use in class, the correct answer is very prominent almost all the time.
Okay, I see. All right, so that gets me to the practical things. You just said that students will run exercise in class, and even if you're running for real quantum computing, so is that something real people can use right now? Your students can actually run on a real quantum computing, or that's something for the future? Are you just using simulators? How is that working?
So there are several companies that have cloud computing, cloud quantum computing. They all have two kinds. They have simulators and they have real quantum computers. Now, whether you want to use a simulator or a real quantum computer depends on a couple of different things, but generally in a class or a workshop we use a simulator because you get the answers back faster.
Okay.
But you can't do really industrial strength. Simulators are limited. If classical simulators could efficiently do what quantum computers can do, there'd be no reason for having a quantum computer.
Right.
So I really like students to get their hands dirty, and during the course of the semester run on some real quantum computers. Sometimes you have to wait a few minutes for the answer to come back. I have had experiences where I had to wait a day or two, but that hasn't happened recently.
Right. And the reason why you have to wait is not because the thing is slow, it's because there's a
lot of people who want to use it. Yeah, absolutely.
Okay. I see. So basically, and how does that work? You pay to run those things? That's free, or
you're looking at the world's biggest cheapskate.
Okay.
There are free tiers and there are paid tiers.
All right.
And my students use the free tier. And I don't think I'm proud to say that I've never paid for quantum computing. The experiments that I do don't use that many qubits that I have to get into this. So, yep, it's free. It's all there.
All right, cool. Now you said one thing that really interests me, because you said that you can do quantum computing with Java, right?
Yes.
So how does that work? Is there like a Java machine running on the quantum computer? Is this like an API that you call?
It's an API.
It's
an API that you call. As far as I know, there are several that have been developed. Johann Voss's Strange API is the only one that's still in development right now. Basically, what you're doing is writing a program that is a classical program, but that instructs a classical machine on how to get the quantum computer to build the circuitry that you want built. Maybe I should say that slightly differently. The programs that I write, the programs that I have students write, the programs that I have in my book, essentially are programs that describe a quantum circuit. A bunch of qubits, what operations are going to be performed on those qubits, what operations will be performed after that, what operations will be performed after that, when this gets fed to a real quantum computer or a simulator, the quantum computer actually puts together those qubits and implements those operations on the qubits.
Okay.
There we go.
Yeah.
And it's doing it in Java, doing it in Python, doing it in any of the other elaborate languages that have been created is, I have to say it, essentially the same thing. You're writing a program that describes a circuit.
Okay. That sounds pretty exciting. Now, you know that I'm always talking about career, right? So, in terms of the developer career, how do you think that's going to play out? So are we going to be like writing algorithms for quantum computing? Are we going to be interfacing with it? So what are the career options there?
In the short term, do something else.
All right.
No, I mean quantum computing won't be front-facing for developers until we have machines that have, I don't know, several thousand qubits.
Okay,
and right now we're not even close to that.
Yes,
We're in the hundreds.
The hundreds, okay.
Depending on who you ask and who you trust.
Okay.
And at the moment, programming quantum computers is a very specialized mathematical task. So there's the math involved, and there's the engineering and the physics involved.
Right. And
probably several other disciplines that I'm unfortunately leaving off. I apologize.
Right.
But it's not something that the average, you take your, I say, you can program a quantum computer in Java, but it's very, very, very specialized thinking about quantum computing. It's not the kind of thing where you're going to worry about the same issues that the typical Java developer worries about now.
Right.
It's going to be a whole different ball game. So if you want to get into quantum computing, which I encourage because I love the subject, action at a distance, as Einstein said, entanglement, superposition, the quantum world, mystery. If you want to get into it, then you're really talking about being immersed in the science.
I see.
Right?
Yeah.
Your developer who wants to program a database is really going to be concentrating on another kind of programming for the near future.
Right. Okay, so let me see if I understand, right? So basically, when you talk about the engineering, right? So there are engineering physicists is still trying to make the hardware.
Yes.
Right, and make that thing work.
Yes.
And grow to thousands of qubits.
Yes, and they're getting there. It's slow, but it's sure.
Right. So that's the engineering part.
Right.
And then just once that thing is solved,
yeah,
then that we can be actually used for it as a software developer.
So I mean, it's sad to say, but the killer app right now that we know of for quantum computing is a malicious app.
Okay.
What Shor's algorithm does is it factors large numbers into primes, and that breaks RSA. And what I understand is that there are hackers right now who are collecting our data, even though they can't decrypt it, in hopes of, within the next several years, being able to decrypt it when they have access to quantum computers. Now, why in the world did I start that line of thinking? I don't know. You asked me a question and I lost track.
No, that's all good,
yeah.
Right? So I'm that's fascinating. Anyway,
yeah.
Right. So
the engineers, well, I
mean, the question was the hardware building, the engineers, physicists building the hardware, and then
yeah.
But I really like the way you went because that's fascinating.
Okay, yeah. I mean, there's a lot of work in the engineering and in the physics, and an equal amount of work in developing algorithms and finding useful ways to use this. One of the things that I like, there's a there's an algorithm that does fairly efficient searching. So if you have 1,000 boxes, and there's a plate of spaghetti in one of them, but you don't know which one, right? Then you want to search through the boxes. What's the worst case scenario? It's in the last box.
Right.
You're gonna have to open all 1,000, 999 boxes, and then you're done. You finally find your plate of spaghetti.
Right.
With quantum algorithm, you can reduce that to 8 searches.
8 searches.
Yeah.
That's impressive.
Yeah. I hope I got that number right, but I think I did. Yes, you're going to take the square root of and divide pi over 4, and I think we're going to get there.
Right,
I think that's what
All right. Okay.
right. And I mean, it's just because of the magic of entanglement and superposition.
Mm-hmm. That's so cool.
Right. I could just see when I call you in the. I didn't. It wasn't 8. I got it wrong. And so, what's going to appear on the screen when you show this to the world is, I'll have said, when you do it with a quantum computer, you get boop searches. You bleeped out the. We did this in class the other day. I'm pretty sure I got the number right.
No, that's all good, right? So you all understand we're having like a informal conversation here. So check out everything that we say here, right? So
Grover's algorithm, right?
Grover's algorithm. Okay.
Yeah.
Very cool. All right, so this is fascinating, Barry. It's so cool, right? And so, this is, in a way, is real world, right? Because you are actually teaching this at university right now,
right?
And you have a bunch of students coming into this course, right?
Right. I don't teach anything because it's real world. I teach it because like you were saying earlier tonight, I'm addicted to learning.
You're addicted to learning. That's cool.
Yeah, and so I pursue anything that's fascinating to me, and this is fascinating to me.
Yeah, it is fascinating.
So,
okay, all right, guys. So so you're having like a little peek here on the life of a couple of Java champions. Actually, the guy here in the front, right? So Vinicius sleeping right there. I don't know. He's right here somewhere, right? So there's 3 Java champions here in this Uber. And we're coming back from the New York Java SIG event, and Barry was really nice to receive us yesterday in the Garden State Java group, and we're now going back to New Jersey, and then tomorrow we fly to San Francisco, right? So very good to be here with you. Thanks, Barry. Thanks a lot, man, for a fascinating discussion.
Thank you. Thank you very much.
Yeah.
This is just on record. Weirdest interview I've ever done in the back of an Uber at night.
Right. Yeah. I think you worked it fine. So thanks, everyone, guys.
Bye-bye.
Bye.